Hello everyone, this is Bill Dees with David H. Paul Incorporated. We're here today with Eli Oakless with FEDCO, and we're going to be talking about energy recovery of RO units using FEDCO turbochargers. And just one second here, I already have an issue. This is going to be a 40-minute presentation. I'm going to start off with an introduction, just going over who's who and also giving a brief background on what we're talking about here. And then Eli will go into the details of what we're looking at today with the FEDCO turbochargers. We will then have a 20-minute question and answering at the very end of the presentation. And that being said, since we're going to have question and answers, we ask you anytime during the presentation, go ahead and type in your questions on the chat box, but we will not answer them until we get to the 20-minute question and answers section at the end of the presentation. This presentation is being recorded. We will be sending out, we will be putting out this video on our website here in a day or two, so anybody can come in and take a look at it at their convenience. You will also be sent out a thank you email with a PDF of this presentation, so you don't have to take notes. You will have that PDF for your records also. It's important to note that David H. Paul Incorporated and FEDCO do not have a financial relationship. We're just presenting this presentation, good, useful information of a topic of interest and value for the water treatment industry. My background, I've been working in water treatment since 1988, specializing in membrane technology since 1999 when I started working for David H. Paul Incorporated as an instructor and consultant. I'm also RO specialist 4 certified through David H. Paul Incorporated. Eli, he began in pump industry in 1980 as manager of an R&D laboratory at Union Pump Company. He's founder and president of Pump Engineering Incorporated from 1986 to 1997, where he developed the Turbocharger, and then in 1997 founded Fluid Equipment Development Company, or FEDCO, where he is CEO and Chief Technologist. Again, questions at any time during presentations, go ahead and type them into the chat box. We'll cover as many questions as possible in the Q&A session at the end. If we have a lot of questions and we run out of time at the end, whatever questions that are left, we will be answering those offline by email. So starting off here with energy recovery, just a background here, the biggest portion of RO operating costs are going to be power. So for example here, with Perth operation maintenance budget, we're seeing power at 41%. That's because these seawater RO systems can operate as high as 1,000 psi or 70 bar of pressure on the feed coming in. Well, with that amount of pressure going through the RO system, it just would not make sense. It would not be cost feasible to operate the unit with all that energy going down the drain. We need to have some way to collect that energy and transfer it back to the front end of it and be able to operate at the higher pressures that are needed. So we need to have these energy recovery devices, and there's 3 basic categories of ERDs. There's a Pelton wheel, turbocharger, and positive displacement. The Pelton wheel, of course, takes the concentrate or waste energy from the RO unit and transfers it into the high pressure pump shaft. So for example, we have these vanes that are directly connected to the high pressure pump, and then we have our reject nozzles forcing the water, aimed the water at these vanes to help turn the shaft of the high pressure pump. Turbochargers and positive displacement ERDs, they're going to take the concentrate energy and boost the RO feed water, but they are not directly coupled to the high pressure pump. So for example, here is a turbocharger showing the impellers for the turbocharger on the right hand side. These impellers now, for example, we have our concentrate coming out, going through the impeller on the left-hand side and then exiting out. Well, that impeller is directly coupled to the input impeller, which then boosts the pressure going to our single stage RO system, or it also, as you can see up here in the right hand corner, the turbocharger can be put in a two-stage system, utilizing it as a interstage booster pump. Here's an example of a large turbocharger installed. There's also, besides this presentation, you can go to FEDCO's website for an excellent animation so you can see exactly how these turbochargers also operate. For the positive displacement type setup, we're going to have our high pressure pump with the low pressure seawater coming in, going through the RO system. Now we have that high pressure reject that we need to reclaim that energy from. There's going to be a device with a piston in there that moves back and forth, and that high pressure reject pushes that piston over, which then forces the low pressure seawater into the front end of the RO system. Well, since we do have a pressure drop across that RO system, we're not going to be able to get up to that higher pressure that the high pressure pump puts out, so there will also be a booster pump installed in there to get up that remainder of the pressure. As a concept here, not exact, just to show you exactly what we're going to have with the positive displacement, we have 4 valves in here with a low pressure. The bottom valves are open. The low pressure seawater comes in, pushes the piston to the right, which the low pressure reject valve is open, which then goes out to atmosphere. We then have the valves automatically switch to the high pressure reject, opens up and pushes that piston over towards the left in this example, and then boosts the pressure up going into our feed water source. This is known as flow serve of Calder to Weir. And then there's also Energy Recovery Incorporated. They have a similar device, but quite different in that it has a rotary type setup with chambers in there in the rotary portion of it, that no pistons. For an excellent video of FlowServe ERD, you can go to YouTube to this link and watch a video on it. And then for an excellent animation for Energy Recovery Incorporated, you can go to YouTube and go to this link and take care of it. So now I'm going to turn this over to Eli, and he is going to then describe the turbocharger setup. Eli?
Thanks, Bill. That's a great introduction. It helps my presentation quite a bit. Basically, we're going to be talking today about FEDCO Turbochargers, plus we'll be taking an overview of other ERDs so we could do a fair comparison between the technologies. In the first page, or first picture, you can see a turbocharger and towards the lower left center of the screen. That's what we'll be focusing on today. First, a little bit about FEDCO, though. Sustainability is kind of like what we're all about in terms of environment. Our facility is geothermally heated and cooled. We use LED lightings. We have 27 of the 32 green building features implemented. We do things like minimizing solid waste, and we're really regarded as the best-in-class manufacturing facility in our region. Sustainability applies to the team. We have numerous initiatives to develop our team's skills and educational levels. We have an on-site fitness center. We do a lot of on-site stress reduction and work-life balance training. And probably the most important thing is we have a safety-first culture throughout the company. And sustainability includes the community as well. We have major events open to the public to promote water conservation. We provide a number of scholarships for STEM students, science, technology, engineering, and math. We have a very high-profile World Water Day observance where we invite the public to our facility to learn more about water. And we sometimes have up to several hundred area elementary and high school students. They submit posters, and we have contests, and we have a lot of fun with water. So we really want to get the word out about the importance of water, water purity, water scarcity out to the public. Quality systems are important, of course. We're ISO 9001, ISO 14001. We have the CE mark for most of our equipment. And something that's not too common in our industry is our test loops are certified by a third party, in SF in this case. We started off as an R&D company way back in 97. It's our 20th year. I guess I should mention that. Excuse me. We have over 15 patents on ERD design and RO system configurations. We have a very active R&D program. a lot of innovation in manufacturing. I guess I should mention that our turbochargers are 100% USA manufactured and supplied. I think that makes us unique for turbochargers. In terms of product testing, all products are tested. We have a number of test loops. The biggest test loop is 2.6 megawatts under VFD control, and it's certified by the NSF to comply with Hydraulic Institute and ASME test codes. So Bill gave us a good summary on energy recovery. So this is kind of like a refresher course from 10 minutes ago. Basically, we have a high pressure pump supplying a membrane. Out of the membrane comes two streams, a low pressure permeate stream and a high pressure brine or concentrate or reject stream. So the brine stream is roughly at the same pressure as the feed stream, and so it still contains a substantial amount of hydraulic energy. An important concept here is what we call recovery. That's the ratio of permeate flow to feed flow, so we need to keep that parameter in mind as we go forward. Okay, so when you don't have energy recovery, this is how the system looks. In this case, we have a membrane that takes about 957 psi of feed pressure. The flow rate is roughly 528 GPM. Out of that membrane array, you have a permeate stream of about 185 gallons per minute, and you have a reject stream of 343 gallons per minute at a pressure that's slightly lower than feed pressure. And with reasonable assumptions on high pressure pump efficiency and high pressure pump motor efficiency, this system would consume about 271 kilowatts of electrical power to operate. So keep that number in mind, 271. Okay, so the question is, how much energy can you recover in an RO system? Well, the chart here shows some relationships. They're approximations because there's a lot of specific variability from system to system. But in general, if we look at a TDS range of our RO system, right, that could range from 5,000 to 40,000. If we look at the feed pressure, which is the green curve, at the 5,000 TDS range, the typical pressure would be about 150 psi. And as we move towards a higher TDS system, let's say up to 40,000, the feed pressure can exceed 1,000 psi. So you can see that energy consumption will go up with higher TDS simply because of the higher feed pressure requirements. If we look at recovery, this is interesting too. At 5,000 and less TDS, the recovery can be up to or exceed 80%. And as we go to higher TDS, the recovery drops down to something close to 40% at 40,000 ppm. So when you put these two curves together and a few other simple assumptions, you get the red curve, which is this red curve represents the amount of hydraulic energy available in the brine stream for each cubic meter of permeate produced. So at the 5,000 TDS RO system, we have about half a kilowatt hour of brine energy available for each cubic meter, half a kilowatt hour, yes, of brine energy for each cubic meter of permeate produced. Go up to 40,000, we have over 4.5 kilowatt hours per cubic meter of permeate produced. So you can see there's almost a 10-to-1 variation in the available hydraulic energy per cubic meters of permeate. So there's a big incentive to use RO energy recovery for high pressure systems. But as we shall see, it also makes sense for low pressure, low TDS systems. Now, a metric that's used to evaluate ERD efficiency is something called transfer efficiency. It's a simple definition. It's basically the amount of energy returned to the RO process divided by the amount of energy available in the brine stream. It's a simple definition, and unfortunately, like many simple things, it oversimplifies the comparisons. So transfer efficiency has led to some misunderstandings and misuse, and we'll be exploring those issues and how to address them. Okay, there are three types of energy recovery devices, as Bill mentioned. The one classification is mechanical drive turbines. This does include Pelton turbines. The next classification is positive displacement isobaric chambers. There's two types, reciprocating and rotary, as mentioned by Bill. And turbochargers can come in two varieties, the free-running turbocharger and the motorized turbocharger. For mechanical drive turbines, we have reverse running pumps, which were initially applied to RO systems, but they're really pretty much out of favor because they have pretty limited efficiency and a narrow hydraulic range. Bill gave a good discussion on Pelton turbines, so we're just going to look at what we call purpose-built turbines or mechanical drive turbines. These are designed for RO applications and for the hydraulic range and experience in RO systems. They generally have somewhat higher efficiency, much broader hydraulic range, and they're usually customized to specific RO installation so they can capture a large fraction of the available energy. And they are gaining acceptance, and generally they're used to drive electrical generators. And we'll be looking at some examples of those a little bit later. So, excuse me, for isobaric chambers, as Bill mentioned, basically use the brine pressing against the feed. There could be a piston, or there may not be a piston, and the two streams may be in contact with each other. Looking at the schematic, we see two pumping chambers. The lower chamber is being filled with low pressure feed, and that low pressure feed is pushing the brine out the drain. And something to note here is that the feed water from your pretreatment system has to be at a higher pressure than your brine disposal. Otherwise, there won't be enough pressure to drive the feed to push the feed, to force the brine down the drain. On the upper chamber, we see high pressure brine pushing feed water out toward the membrane, and then that feed water needs to be boosted in pressure to match the membrane pressure. A couple of things to remember. And one important thing is isobaric chambers cannot regulate feed pressure. The high pressure pump establishes feed pressure. Okay, we're going to be looking at rotary isobaric chambers in a little bit more detail. They're pretty common in many applications, so we'll take a little bit deeper look into their operation and their characteristics. Here we see a picture of an installation. There's 4 of these rotary isobaric chambers in that installation. And to the right, we see a simplified schematic of the isobaric system. The rotary isobaric chambers only comprise a portion of the total system. We know that there's a high pressure booster pump, there's some control valves, usually there's 2 precision flow meters, there's 4 manifolds, a high pressure feed, high pressure brine manifolds, low pressure feed, and low pressure brine manifolds. There's other instrumentation as well required to operate the system. So it isn't just isobaric chambers that we're talking about. We're talking about the system that is needed to make these chambers work. Important point here is that they pump a side stream of the feed, so they operate in parallel with the high pressure pump. So the isobaric chambers reduce the capacity of the high pressure pump. As I mentioned, there's a lot of auxiliary equipment, and for whatever reason, isobaric chambers of the rotary variety seem to be limited to about 300 gallons per minute. They've been at that size range for many, many years, and that seems to represent the highest available capacity that is certainly currently out there, or that may be out there in the near future. So that's for this example here, we see 4 units simply because the brine flow requirements exceeded the unit capacity, so they needed 4 units in this case. This chart here, or this graph here, illustrates how they function. It's a little bit hard to explain, but I'll do my best. If you look at the left cutaway, we see a dashed line that runs vertically through the casing of the unit. The left side of that line is the low pressure side of the isobaric chamber. The right side is high pressure side. We see passage A. Passage A is accepting, at this point in time, accepting low pressure feed. That low pressure feed is pushing the brine out to the low pressure brine outlet. On the right side, channel B, high pressure brine is driving feed water toward the membrane. So you got these 2 fluid interfaces that ideally are 180 degrees out of phase, although there's no actual positive control to regulate their position. So the key here is that before the fluid interface on each side of the unit reaches the exit, that the rotation of that orange section, that rotor, will have carried the chamber over to the opposite side, and then they'll be subject to discharge by the corresponding stream. So if we look at channel A on the left side, it's now being filled with low pressure feed. Ideally, rotation will carry that channel to the right side of the unit before the fluid interface escapes from the unit. And the same applies for channel B. So you got these 2 channels, ideally 180 degrees out of phase. There's a lot of sensitivities. What controls the fluid interface of position is a high pressure booster pump and a control valve on the brine discharge. So that's where the high pressure flow meters come in, and you regulate this until you can minimize the amount of brine feed mixing. And that is an issue with these units. There's always brine and feed mixing occurring. So feed water is absorbing some of the brine is diffusing into the feed water and entering the membrane array. So typically, the feed TDS of a system using a rotary isobaric chamber is higher than the TDS of the feed water coming into the system. Something called rotor blow-through may occur where the interface escapes the unit, and then you have a very high degree of brine entering the membrane or a high degree of feed water going down the brine drain. There's a lot going on here. I hope that didn't confuse anybody, but the illustrations, I think, are hopefully self-explanatory. Here's an array of isobaric chambers here. Again, the reason for the number of units is because of limited capacity. But I have to say that the fact that they could be ganged together allowed the isobaric chamber to be adopted fairly early as mega project seawater RO systems were being built. ERD such as a turbocharger, which only requires 1 unit per train, we had to go through many years of successively larger and larger units to prove out our reliability and efficiency. The very good news, though, is that the turbocharger has now been installed and is operating successfully on the biggest RO trains in the world. So we are now where we need to be in terms of bringing this technology to all RO systems. Okay, there's 3 types of turbochargers offered by FEDCO. There's a free-running turbocharger, there's a motorized turbocharger, and then there's a high-pressure turbocharger that's meant for hazardous applications or the ultra-high pressure applications. We're going to be focusing on the free-running and a motorized turbocharger for RO applications. Here is a turbocharger in a system, an upper left illustration. As we explained before, the intermediate pressure from the feed pump is boosted to the membrane pressure by the turbocharger, and the brine stream coming off the membrane entirely powers the turbocharger for producing that feed pressure boost. You can see on the right side, a cutaway of a turbocharger. There's basically a rotor which has a pump impeller on the left end and a turbine impeller on the right side. There's a shaft connecting the two, of course. There's a diffuser that wraps around the pump section, and there's a center bearing which supports the rotor, and that's lubricated by feed water. And there's basically one end cap to this unit. It's a very simple unit, very small footprint, and as mentioned earlier, there's absolutely no auxiliary equipment. So this turbocharger, it comprises the entire ERD system, and as we shall see, the efficiency is quite high as well. Okay, what this chart here shows is the blue portion shows the range of FEDCO hydraulic turbocharger operating range. We go from down to about 6 cubic meters to up over 3,000 cubic meters per hour of feed water. Our smallest unit actually in the field is 8 cubic meters per hour of feed water. Our largest is about 2,600 cubic meters, or nearly 12,000 GPM of feed water. And the pressures typically run 65 to 70 bar. Our highest pressure unit is 150 bar. So you can see we cover a very big hydraulic range with our equipment. It covers all the applications above basically 4 cubic meters to 5 cubic meters per hour, up to the largest systems in the world. Okay, going back to our first example, if you stuck a turbocharger between the high pressure pump and the membrane, then the high pressure pump discharge pressure is reduced down to 33 bar. If you may recall, it was 66 bar. So basically the turbocharger cut the required pump pressure by 50%. So now the power consumption of the pump is 135 kilowatts. The turbocharger is totally automatic. There's not one bit of adjustment required to start the system. Simply start the high pressure pump, and turbocharger generates the boost automatically. We can discharge brine against any back pressure. There's no linkage between brine discharge pressure and the feed pressure. There's no brine intrusion into the feed stream under any operating mode. And of course, the high pressure pump and motor and VFD or motor starter in this example is reduced by 50% in its rating. So it's a big CapEx savings as well. Okay, so what do you look at when you select a turbocharger or select an ERD? Well, let's say the people who have experience, the first thing they look at is reliability. They look at ease of installation, ease of operation, ease of maintenance. They look at energy savings, and ERD safety is at the end of this list, although it's the most important. The reason it's at the end of the list is we need to discuss some features first before we could talk about safety. Okay, the rotor of the FEDCO turbocharger is unique and patented. It's a one-piece rotor, very rigid. The first critical speed is well above the maximum operating speed. These units are custom built to each individual system requirement. So we developed a very extensive array of design software and machining software that takes basically an RO projection and turns it into CNC program code, where we produce an optimized hydraulic flow path for the turbocharger both on the feed and brine sides. This rotor includes a diffuser wrapped around the pump impeller, And we use what we call the rotor flow lubrication system to bring feed water to lubricate the thrust bearing, which is located on the outboard face of the turbine impeller. And there's many technical advantages of using this rotor flow lubrication. And we'll discuss some of those a little bit later. Now we dynamically balanced, as you can see here, you can see a picture of a FEDCO rotor on the left side. On the right side, you see a rotor from another supplier. The FEDCO unit is a one-piece construction machined from duplex or super duplex stainless steel. The rotor, which is really my original turbocharger design way back in the day, uses multiple pieces, and I'm almost embarrassed to look at it now. I shouldn't be that, but it uses there's a stud attached to the turbine shaft. There's a keyway and a key to secure the turbine to secure the pump impeller to the rotor, and there's a retaining nut. Couple big problems. One is you have to have clearances to assemble this unit, which means you cannot maintain a high degree of dynamic balancing in this unit because of the looseness. The closed clearances create potential crevice corrosion sites. There's a long overhung length between the pump impeller and the location of the center bearing, and we'll be talking about why that is important in a moment. And there's also shaft shoulders, and the stud creates areas of stress concentration, which can and do fail. We mentioned the rotor flow lubrication. You can see here an illustration of the rotor showing the internal passageways. It takes precision machining and a really a highly skilled machine shop to do this kind of work, but it's something we do every day. This has worked out extremely well for our units. We use this same design from our smallest units, handling 6 cubic meters, to our biggest units, handling up to 3,000 cubic meters per hour. A lot of advantages, and among them eliminating external lubrication lines, which we'll be talking about in a minute. Okay, we mentioned the diffuser being wrapped around the pump impeller, and why is that so important? Well, when you have a diffuser, there's many channels of flow for that diffuser. That results in a symmetrical pressure field around the pump impeller. So even when the unit is off design, there still will be a symmetrical pressure field, tangential pressure field around the pump impeller. So the pump impeller would not be exposed to unbalanced radial forces. But if you use a single volute, as illustrated on the right side, when that impeller is running at off-design speed, which is actually the norm in RO systems, off-design operation is quite typical, there will be side forces imposed on that impeller by non-uniform pressure field around the pump impeller. And you can see an arrow pointing towards the 10 o'clock position. That's what happens when the flow rate through the turbocharger is below the design point, or the RPM is above the design point. It's a couple ways of looking at it. And if the flow is high, then the force vector points towards the 6 o'clock. What's important here is that the center bearing, which is product lubricated, which doesn't have a high degree of low carrying capacity because it is feed water acting as lubricant, will become oval or egg-shaped. We've seen this many times. When the turbocharger operates at off-design condition with a single volute, you get an oval or egg-shaped center bearing. We talked about the rotor flow design. Well, one of its benefits is it eliminates the external tubing used on other turbochargers. And these external tubes are a hazard, a safety hazard, plus they represent maintenance items as well. You can see that on the unit on the left, there's a high pressure tube which handles feed water for the thrust bearing lubrication. And on the right, you see a high pressure tube with a valve, a quarter turn ball valve, that handles high pressure brine. So both of those represent leakage potential, they represent maintenance potential, and frankly hazards. The state-of-the-art turbocharger has eliminated all external fittings and tubing. Turbochargers are easy to install. You hook up 4 pipes, the brine inlet and outlet, the feed inlet and outlet, and that is the end of the installation. There's no auxiliary equipment, no pumps, no boosters, no manifolds. That's it. You can see a very small unit installed in the upper right photo, and right next to a membrane housing, and you can see another unit tucked into a small space near the membrane array. Turbochargers can be operated in any orientation. They can be placed anywhere in the RO system. They can operate in the dirtiest, dustiest environments, could even operate underwater. The same story holds true for large turbochargers. Again, it's hooking up 4 pipes, and that is the extent of the installation. Here we see a very large turbocharger. This is handling 1,650 cubic meters per hour, or about 9 or 10,000 GPM for a seawater plant in the Middle East, 68 bar feed pressure. So even the very largest turbochargers maintain the same simplicity of operation and installation. We talked about, one of the functions of the turbocharger is to regulate brine flow and pressure. And the turbocharger does it this way. The turbine section has two nozzles. There's what we call the main nozzle, which is sized out during the manufacturing of the turbocharger based on the customer operating point or points. And then there's a secondary nozzle, which we call the auxiliary nozzle. This nozzle is controlled by an external valve, what we call the auxiliary nozzle valve. The upper left illustration, we see the auxiliary nozzle valve is closed, which means that the brine must flow only through the single main nozzle. This would represent an application where brine pressure is low or brine pressure is to be maintained at a high level. But if you need to increase brine flow or reduce brine pressure, you open up the auxiliary nozzle valve, which allows an additional flow path for the brine through the auxiliary nozzle. The important point here is that the total brine flow still passes through the turbine impeller, and thus the total energy is recovered from the brine stream. The right graph shows a typical range from the auxiliary valve being closed, the auxiliary valve being opened, and that range is more than ample to cover the normal pressure range or flow variation in seawater RO systems. Okay, this is where we're going to learn how to operate a turbocharger. This is it. This is, in one sense, the operating manual for a turbocharger. To increase brine flow, open the auxiliary nozzle valve. To decrease brine flow, close the auxiliary nozzle valve. That's it. That's the end of the education. And it's actually quite important because when a plant is commissioned, you have plenty of training. Everybody's excited. Everybody knows how to run the plant. But after a few years, plant personnel change. If you have a complicated ERD system, you're going to have to do a lot of training on the new plant people, and they're going to go through a learning curve. With the turbocharger, this is the instruction. Open the valve or close the valve. Very, very simple. There's nothing really an operator can do to harm the system through misoperation of the turbocharger. Maintenance is equally easy as operation. Remove the end cap. You push out the rotor cartridge, push out the thrust fairing, and to install a new new thrust fairing and rotor cartridge, you simply push them in by hand. A small turbocharger can be overhauled in 10 minutes. A large turbocharger may take an hour to overhaul. It could be overhauled by plant personnel. There's no skills required, no shims, no precision measurements. Simply undo the end cap, push out the old, push in the new, and that is it. We talked about transfer efficiency and how it's in some ways useful, but it's also misleading. And so what we do is apply normalization correction factors to transfer efficiency to account for the differences in ERD operation between isobaric chambers and turbochargers. If you don't do that, you'll be comparing apples to oranges or apples to pineapples, but you won't be comparing the same efficiency. So this table kind of walks us through how to normalize transfer efficiency. For the rotary isobaric chamber, starts off great, 95% transfer efficiency. The highest turbocharger efficiencies we've obtained so far are 84%. Now, we talked about the brine feed mixing in an isobaric chamber. Well, that's going to raise osmotic pressure because of the higher TDS of the feed stream. And when you run membrane projections to gauge that impact, it results in about a 3.8% increase in operating pressure. So that loss has to be charged against the isobaric chamber. Large isobaric chamber systems have extensive manifolds and valves. We assume 1% pressure loss on the feed side, 1% pressure loss on the brine side, manifolds and valves. Excuse me. And so we say a 2% loss of energy in the manifold and valve array. We mentioned that the isobaric chamber pumps a side stream or operates in parallel with the high pressure pump. That means that the high pressure pump is handling a smaller feed flow than the feed to the membrane. In contrast, the turbocharger feed pump handles total flow, but at reduced delta P. So the situation is with the isobaric chamber, the high pressure pump handles a reduced feed flow at maximum feed pressure. And as I just mentioned, the turbocharger is handling full feed flow at a reduced delta P. And a fundamental characteristic of centrifugal pump design and operation is they're more efficient when handling high flows and low delta P. on average, the efficiency hit caused by using a rotary isobaric chamber is about 4%. The isobaric chamber also requires a booster pump. The extra energy associated with that booster pump is about 1% to 1.5%. The last factor that needs to be considered is the fact that isobaric chambers cannot regulate feed pressure. Only the high pressure pump can regulate feed pressure. So when using an isobaric chamber, you have to use a VFD on the high pressure pump, or you have to oversize the pump and use a feed throttle valve. There's a version of the turbocharger that does not require any sort of feed pump regulation. So it does not, is not subjected to the energy loss associated with feed pressure control. And when you multiply out all these factors, that 95% for the rotary isobaric chamber becomes about 81.6 to 82%. And for the large turbocharger, 83.8. So you can see how you have to normalize the transfer efficiency. You have to account for the impact of the ERD on system operation. You cannot look at the ERD in isolation, otherwise there'll be misleading and frankly mistaken conclusions made about which ERD would perform best in an RO system. 84% is pretty darn good efficiency. To achieve that, we have to have very excuse me, high component efficiency. And so we do that by machining our impellers, our rotor from bar stock. So we have precisely machined rotor geometry. Of course, the rotor is highly optimized using validated computational fluid dynamics analysis. We can pick the speed of operation so we can get optimal specific speeds. And for instance, the rotor pitch here has a 91% efficiency on the pump end at 7,000 GPM, and on the turbine end, which is the brine end, it has 91% efficiency as well, handling about 4,000 GPM of brine. And so in this case, the transfer efficiency is about a little bit over 82%. ERD safety, certainly last but not least, with the isobaric chamber, with the turbocharger, it has 3 high pressure connections. With the isobaric chamber in a large system, you may have over 100 cut groove pipe joints. Mechanical seals, 0 for the turbo, several for the rotary isobaric chamber. High pressure valves, none for the turbo, numerous for the isobaric chamber. Leakage potential, 0, virtually 0 for the turbo. And for the isobaric chamber, because of the hundreds of pipe joints, it's extensive and pervasive. Noise in a large system, less than 85 dBA from the turbo, and it's coming from a small source, a small component. With isobaric chambers, it can be over 100 dBA simply because there's so many units running and so much emitting area from the units themselves plus attached piping. So it's a large emitting area which would be difficult to attenuate. So cost is no object. We use what kind of ERDs are used, where reliability, ease of operation, performance are critical. Well, it turns out to be the turbo. Whether it's offshore platforms, military systems, cruise ships, factory vessels, it's the turbocharger. All right, now we're going to be looking at motorized turbochargers. There's 2 types. The one on the low left is designed for seawater conditions, and the one on the right is designed for brackish conditions. And so what does the motor do? Well, it does this. We're looking at a seawater RO system with a highly variable pressure requirement, 70 bar during the winter, 50 bar during the summer. So how do you get that pressure? Well, you get about 2 bar from the pre-treatment system. We're using a motorized turbocharger, so what that means here is that the feed pump doesn't have to produce a variable pressure output. It runs, in this case, it will deliver a constant 30 bar discharge pressure. There's no VFD on the high pressure pump, and there's no feed throttle valve anywhere in the system. So the motorized turbocharger will then modulate the rest of the pressure. So you can see here that the turbocharger produces 40 bar during a boost during the wintertime, 20 bar during the summertime, and the energy for that boost comes primarily from the turbine section of the turbo, and then the balance is made up by the motor from the motor that is attached to the turbocharger. Okay, we're going to be looking at interstage pressure boosting briefly. Interstage pressure boosting is used in brine stage systems. It really does a good job for flux balancing, reduces fouling potential, can extend membrane life, can increase recovery, and it can reduce energy consumption. The ideal way to do pressure boosting is to have a double duty device. In this case, we're using a turbocharger to do the boosting and to recover brine energy. So what makes energy recovery practical on these low pressure systems is that the ERD is doing 2 duties, energy recovery and pressure boosting. The motorized turbocharger provides a greatly enhanced performance because now the motor can be used to precisely control the interstage boost pressure amount, and it also, of course, recovers all the available brine pressure. So it really is a neat system. It allows a combination of unexpected conditions, provides precise control over the second stage operating conditions as well. Here's a couple of cases of motorized turbochargers. The one on the left is in Singapore at the Changi New Water Facility. There's 10 of these installations of these units. I believe this is a 220,000 ton per day output system. And they're building another identical plant, which will be using 10 more of these same designs. In the new plant on the right, we see an installation in California for also a water recycle facility using, again, the motorized turbocharger. We talked about mechanical drive turbines, the purpose-built mechanical drive turbines. So you see 3 FEDCO products here. There's a turbine generator in Port Hueneme, California, recovering excess hydraulic energy turned into electricity at a membrane plant. There's turbine generators at a Spanish RO plant recovering the hydraulic energy from the brine stream. And the rightmost one is in Scotland, but it's not an RO facility. This is actually in a water distribution system. Apparently the system is at the bottom of a hill. Instead of, they had a pressure reduction valve, so we said, let's put a turbine generator in there. It's been installed, it's been running for years, it's working great. So that's another non-RO application for energy recovery for water distribution systems, especially in areas with a hilly terrain. This is the most important slide of the show. It shows all the factors that you have to consider in an energy recovery device. Energy recovery devices do one good thing, they reduce energy consumption, but they increase installation costs, initial costs. There's more training. There's interest charges on the financing of the plant to cover the ERD costs. They add the maintenance, they add the downtime, and of course when the plant is eventually decommissioned, there'll be extra costs associated with decommissioning the plant's ERDs. So you have to really think about what energy recovery device should be selected. And a question that's often asked is, what ERD should I use? The rule of thumb would be to use the ERD which has the lowest CapEx and impacts the system in the least negative way possible. You don't want the ERD to compromise membrane performance. You don't want the ERD to add to customer or to operator training. You don't want the ERD to increase the downtime potential. So the default answer is go for turbocharger, but if there's something else, if there's other factors, then certainly consider all ERDs. It's our responsibility as responsible designers of water treatment systems to look at all options, but the rule of thumb is go with the simplest and least impactful type of ERD. And that brings us to the end of the presentation. Thanks for your attention. I hope I didn't talk too fast. Thank you.
Okay, Eli, I really appreciate that very excellent presentation. And now we're going to open it up to question and answer portion of the presentation here. And of course, Eli will be answering. He'll read the questions that you are typing into the chat box, and then he'll answer your questions. Eli?
Okay. Let me see. The question is, are your castings poured in the U.S. as well? For the turbochargers, yes, we use local suppliers in the Midwest for our castings. Can the auxiliary valve be automatically actuated to highly variable influent TDS applications? It certainly can be automated. Many of our larger turbochargers are equipped with valve actuators, multi-turn type, and the valve actuator, or excuse me, auxiliary nozzle valve does have a fairly wide range of hydraulic variability. In seawater applications, it's almost always sufficient to cover the most extremes of conditions. In brackish systems, it can become more challenging because the ratio of pressure changes and the ratio of recovery changes in brackish systems are often much higher than in seawater systems. So in the case of in highly variable applications, we may need to use extra equipment to handle highly variable brine flows and pressures. But for typical seawater systems, there's no additional equipment required. Must all the brine pass through the turbocharger? The answer is no, but why would you bypass brine? It's energy that can be recovered. If some process condition may require a portion of the brine, that's absolutely fine, no issues. Since turbochargers are handling high TDS, what is the lifetime guarantee by FEDCO? Our turbochargers have a 3-year warranty, which I believe is the longest in the business. What limits the lifetime of such equipment is corrosion of the materials. So if the proper materials are selected, then the turbocharger lifetime will be indefinite. One thing we've learned is that don't go conservative on materials. Super duplex is always safe to use. Duplex is okay for lower TDS seawater or high brackish applications, but if you make the right material selection, a turbocharger lifespan can easily be 15, 20, or 25 years. It really comes down to the corrosion limits of the material. What is the most efficient recovery for seawater RO turbos? Is it constant from the smallest up to the largest unit? No, the efficiency does vary. With smallest units, efficiency, the transfer efficiency may be the mid-60s. The largest units, it's up to 84%. We're always making efforts to improve the efficiency, and we're focusing on the smaller units now with the new rotor geometries, but the efficiency does increase with larger sizes, for sure. For turbochargers, please advise, do you have a preferred type of pump, either vertical or multi-stage? There's absolutely no preference in our regard. You can use vertical pumps, horizontal pumps, multi-stage, single-stage, reciprocating positive displacement pumps. No matter what, all we need is a source of feed water. It doesn't matter where that source comes from, as long as it's at the required pressure and flow. What is the standard recommended service maintenance procedure for a turbocharger? What should the operator be watching out for? Well, we would suggest an annual inspection of the thrust bearing. It's not necessary, but we would suggest it at some convenient point during plant maintenance. As we saw from the illustration in one of the slides, an inspection will literally take on a small unit 15 minutes and a mega unit an hour. That could easily be accommodated in a routine outage. I guess the question regarding what would an operator look for, they would look for a reduction in turbocharger boost. Now, turbocharger boosting will vary based on brine pressure and brine flow and overall system recovery. So they need to be mindful of those effects on boost, but if the boost appears to be lower than normal, there should be an inspection done at a convenient time. Is it necessary to bypass the turbo during cleaning and flushing? That's a very often asked question, and the answer is no. The flushing fluids can pass through the turbocharger, but be mindful that the turbocharger will impose some flow resistance. So although you do not have to isolate the turbocharger, you may want to have an additional bypass around the turbocharger to reduce the pressure drop of the cleaning fluid as it moves towards the membrane. So the question, this depends on what your cleaning flow rate is or your flushing flow rate is, how much pressure drop you can tolerate through the turbocharger, and what is the pressure capability of your cleaning pump. But the important question, or a point here, is that you do not have to isolate the turbocharger from the cleaning solution process. What happens if a 120 cubic meter per hour turbo is used for 80 cubic meter per hour feed flow? Well, it's really the brine flow that matters. The feed flow can vary quite a bit. By assuming that, you mean if the brine flow is similarly reduced? Well, if you're reducing the brine flow, of course, you close the auxiliary nozzle all the way to maximize the flow resistance or minimize the CV of the turbine. And then after closing the auxiliary valve all the way, and you still do not have enough delta P across the turbine, you have a couple of solutions. One is you can apply back pressure to the turbocharger, the brine line, or we could provide a new rotor for the unit. But the best thing is to tell us in advance what the hydraulic range will be, and then we could design into the turbocharger accommodations to meet your requirements. So the best thing to do is anticipate the requirements. And if you do have a very wide range of brine flows, we will do special designs to increase the auxiliary nozzle range of flow and pressure. So if you know about a big variation, tell us in advance, and we'll make sure that the turbocharger can accommodate that to the highest possible degree. For motorized turbochargers, do you have in your range motors suitable for hazardous area applications for use in refineries? Well, our turbochargers are used in refineries. In terms of the motor, whether it has the proper rating for operation in explosive atmospheres, we have provided a motorized turbocharger in such an application. The only requirement, we'd have to check with the motor supplier to make sure that they can provide a suitable motor for a hazardous environment. So we'd have to check with the motor supplier, but in principle, the answer is yes, we could use the motorized turbocharger with a suitably rated motor in a hazardous environment. What is the most reasons of getting the end thrust damaged, the wearing in the turbocharger? The thrust bearing is located on the outboard face of the turbine impeller, and what can harm that is debris. If debris gets into the feed water, and the feed water, now we use a blockage device to in our rotor flow to deflect debris. So it's a pretty rare event, but if debris should enter the turbine section and the debris gets between the thrust bearing and the turbine outboard shroud, the bearing can be damaged. A turbocharger can operate for a long time with a damaged bearing. There will be some loss of performance, but really if the bearing is not replaced in a reasonable amount of time, the rotor face can be damaged, which would require remachining and to renew the surfaces. So it's usually debris that can damage the bearing. In the past, there's other factors that can damage the bearing, but the rotor flow design has addressed that those issues. So nowadays, it's basically debris in the brine stream or debris that can get through the filtration into the lubrication passages. What is a typical delivery period of turbochargers for GCC countries? Very quick. One nice thing about turbochargers, among many, is that they're small and lightweight, so air shipment is easy. If you need a turbocharger quickly, we could design, build, test, and ship a turbocharger in 4 weeks. And air freight is typically about a week, including customs duties and delays. So we could get a turbocharger out to the GCC in 5 weeks. My feed order has a high TDS of 500 milligrams per liter. Is it advisable? Oh, I'm sorry. My feed order has a TDS of 500 milligrams per liter. Is it advisable to use a turbocharger? The best way to answer that question is to provide us with your membrane projections. We'll review the projections. We're assuming that you'd be using a brine stage system and would focus on installing a turbocharger between the first and second stages. We have application engineers who are very familiar with RO membrane projections and who have indeed designed RO systems themselves, so they could definitely be a good assistance for you in optimizing your membrane array for energy recovery. So 500 milligram can be a suitable candidate for energy recovery, but we need to see the membrane projections to best answer that question. Does FEDCO offer high pressure pumps as well? Oh, yes, we do. We offer the complete package. We offer high pressure pumps from 6 cubic meters per hour, excuse me, up to about 1,500 cubic meters per hour. And these pumps are, optimized for seawater and brackish water RO conditions. We're not making general purpose pumps that we could sell in other industries. Our pumps are designed for RO. So what does that mean? That means that our hydraulic passages are designed for efficiency and not necessarily for cavitation, because in RO applications there's usually ample NPSH available. So we design our flow path for maximum efficiency. We design our delta P to accommodate the turbocharger, although we do sell high pressure pumps that could develop full membrane pressure. without a turbocharger. And of course, our materials of construction are duplex, super duplex, and Xeron 100. Our pumps are single stage, multi-stage, vertical, and horizontal. They're all centrifugal type, of course. Under which conditions do you recommend a motorized turbocharger? For seawater applications, it's for larger systems where the flow rate is above about 500 cubic meters per hour of feed per train, which corresponds to roughly a 5,000 ton per day train, 5,000 ton and larger. For brachy systems, motorized turbochargers can be used for almost any capacity of system, for very relatively small to the very largest. So the most important point to remember here, though, is for seawater systems, as a rule of thumb, 5,000 ton per day trains and larger would all benefit from the motorized turbocharger. Using the A and V after closing or opening found no significant brine flow change. Can you advise why? Well, when that happens, that usually means you're not adjusting the feed flow. The turbocharger, unless it's motorized, but if it's not motorized, the turbocharger cannot regulate the feed flow. So when you open up the ox nozzle, you're increasing the brine flow through the turbine section, which means you're getting more boost. So if you think you're going to reduce the brine pressure or the membrane pressure by opening up the ox nozzle but not adjusting the feed side, it's not going to happen, or at least it's not going to happen to the expected degree. So you have to regulate both streams. You have to regulate the feed stream by using a VFD on the high pressure pump or throttle valve, and then and so that establishes the desired feed pressure and flow, and then the turbocharger will be used to establish the desired brine flow and pressure. So I suspect that what's happening here is that the feed stream is not being adjusted. So, but if you have more details, we can answer that via email. Okay, I see that was the last question. So I hope I covered them all adequately. If there's more questions later, we'll be certainly happy to answer them through email, or feel free to call us as well. Thanks a lot.
Thank you, Eli. We really appreciate the presentation you gave us. And if anyone in the attendance has any more questions, whether it's for FEDCO or for us, please, of course, contact us. If your question wasn't answered during the Q&A session, you will get an answer from us by email. If you have any other questions, like I say, please contact the presenter, and then also you can contact us for our training or consulting. Thank you again for attending. As the attendees are leaving, we ask you to take 10 to 30 seconds to answer 3 polling questions as you're leaving, so that we can, of course, get new topics and get better at our webinars. Thanks a lot. Bye.